The ground moved in 3 places at once this week: Japan, Fiji, Nevada, 3 separate zones, 3 separate tectonic settings, all showing unusual behavior inside the same 72-hour window. All of it under a blood moon. That's the headline. Here's the story underneath it. While everyone was watching those 3 zones, a team of scientists quietly published a study that rewrites everything we thought we knew about the Cascadia subduction zone, the fault behind the big one. 13 years of secret seafloor data. One conclusion nobody was expecting. The fault isn't one fault. It's several. Some locked, some leaking. One aimed directly at Seattle. By the end of this video, you'll understand not just what's happening right now, but why the answer to how bad could it get just became a lot harder to answer. Subscribe and follow along, because the ground is still moving. 3 zones are still active, a fault system just got a lot more complicated, and the researchers watching the Pacific Northwest seafloor are not done talking. When the next finding lands, this channel breaks it down first. You'll want to be here. Now, let's get into it. Something is wrong with the ground beneath our feet, and 3 different parts of the planet decided to announce that fact at almost exactly the same time. Not one region, not 2. 3 separate seismic zones spread across thousands of miles of ocean and desert all began showing unusual activity within a 72-hour window. And if that's not enough to make you sit up a little straighter, consider that all of it happened while the moon turned blood red in the sky above half the world. Let's start with the numbers, because the numbers are where the story lives. In the Ryukyu Islands, the arc of land stretching from southern Japan toward Taiwan, over 1,200 earthquakes have been detected since February 26th, 2026. Not 12, not 120, 1,200. The swarm has already produced events at magnitude 5.0, 5.1, 5.2, 5.4, and then a peak of magnitude 5.6. That sequence matters, and we'll come back to why in just a moment. Meanwhile, south of Fiji in the Tonga-Kermadec trench system, 3 separate earthquakes have struck in roughly 3 weeks. Magnitude 6.2 on February 10th, magnitude 6.0 on February 22nd, magnitude 6.3 on March 1st. Each one roughly as powerful as the last, or stronger. But the detail that makes seismologists genuinely uneasy isn't just the magnitudes, it's how far down these earthquakes are occurring. We're talking 500 to 600 kilometers underground. That's not a surface crack. That's not a shallow fault slipping beneath a city. That is the mantle, and earthquakes are not supposed to work the way they work down there. And then there's Nevada. In the Warm Springs area, east of a town called Tonopah, a swarm of over 100 seismic events has been rattling the desert floor. The largest so far reached magnitude 4.3 on March 2nd, with additional events at magnitude 4.0, 3.9, and 3.5. Small by global standards, but scientifically significant for one very specific reason. When researchers at the Nevada Seismological Lab looked at the data and tried to match it to a known fault, they came up empty. The fault causing this swarm didn't exist on any map before the swarm started. So you've got a swarm in Japan that's still building, earthquakes in the Fiji region getting progressively stronger, and a brand new fault materializing out of the Nevada desert. And all of this happened within the same approximate window as the total lunar eclipse of March 2nd through 3rd, 2026. A blood moon that lasted 58 minutes at totality and was visible to approximately 3.3 billion people. The internet, predictably, connected every dot it could find. Here's where I want to be honest with you, because this channel earns nothing from manufactured panic, and I'd like to keep it that way. Earthquakes happen every single day. The United States Geological Survey typically detects somewhere between 12,000 and 14,000 earthquakes every single month worldwide. Most are too small to feel. Some days produce clusters simply because the conditions were right in a particular region. The appearance of a pattern doesn't prove the existence of one. Humans are, unfortunately, pattern recognition machines who will see constellations in random stars if given enough time and a dark enough sky. But here's what I also know. Some patterns are real. Some clusters are not coincidence. And the question of whether regional seismic stress can propagate across plate boundaries and influence distant fault systems is not a fringe question. It is an active, contested, and genuinely unresolved area of modern geophysics. So we're going to hold both things at once. We're going to look at the evidence carefully, follow the science as far as it actually goes, and resist the urge to leap past it. That's the deal we make on this channel. The deeper story here, though, the one that actually justifies the level of scientific concern being quietly expressed right now, isn't any of these three zones. It's a study published on February 27th, 2026. A study built on 13 years of data collected from instruments sitting on the floor of the Pacific Ocean. A study that looked at the Cascadia subduction zone, the fault system that scientists believe is capable of producing a magnitude 9 or greater earthquake along the coast of the Pacific Northwest, and found something that fundamentally changes how we understand what that fault is doing right now. But to understand why that discovery is significant, you first need to understand what's happening in Japan and why a swarm that's still building is more interesting than one that's already peaked. The Ryukyu Island arc is one of the most geologically active stretches of real estate on the surface of this planet, and that status is entirely earned. The arc curves through the East China Sea from the southern tip of Japan's Kyushu Island all the way toward the northern coast of Taiwan, a chain of islands sitting directly above one of Earth's great subduction boundaries. Below this arc, the Philippine Sea Plate is grinding northwestward and being forced beneath the Eurasian Plate along what's called the Ryukyu Trench. This process has been going on for millions of years. It built the islands, it fuels the volcanism, and it generates earthquakes constantly, reliably, and in large numbers. Earthquake swarms are, in fact, common here. If you pulled up the seismic record for the Ryukyu region over the past few decades, you'd find clusters of activity scattered throughout, most of which faded after a few days and were forgotten by everyone except the researchers who cataloged them. So why is this particular swarm drawing attention beyond the usual monitoring reports? The answer comes down to a detail that experienced seismologists notice immediately. The sequence is escalating instead of declining. Most earthquake swarms follow a recognizable pattern. They begin with a relatively strong event, sometimes called the main shock, and then produce a long tail of smaller aftershocks that gradually decrease in frequency and magnitude over days or weeks. The energy front loads. The system releases stress, and then quiets. What's happening in the Ryukyu swarm is different. The sequence has moved through magnitude 5.0, 5.1, 5.2, 5.4, and then 5.6, the largest event arriving after the swarm had already been running for days. The system isn't releasing energy, it appears to be accumulating it. There's a concept in seismology worth understanding here called cumulative seismic energy. When you add up the energy released by all the smaller events in a swarm, you get a running total. Now consider this. A magnitude 5.6 earthquake releases roughly twice the seismic energy of a magnitude 5.4. It releases about 32 times the energy of a magnitude 4.6. That single 5.6 event, coming at the end of this escalating sequence, approximately doubled the total energy the swarm had released up to that point. It didn't represent a release and a calming. It represented the system reaching a new threshold. This is the part where seismologists get genuinely cautious, and where context becomes critically important. Certain major earthquakes in the historical record were preceded by foreshock sequences that, in hindsight, showed exactly this pattern. The magnitude, 9.1 Tohoku earthquake in Japan. In 2011, the one that generated the devastating tsunami was preceded by a foreshock sequence that included a magnitude 7.2 event 2 days before the main rupture. The magnitude 8.8 2010. Mal earthquake in Chile was preceded by swarms in the region. Scientists have studied these precursors carefully, looking for reliable warning signals. And here's the part that keeps earthquake scientists honest. The overwhelming majority of swarms that look like foreshock sequences turn out not to be foreshock sequences. They're just swarms. The stress releases gradually, the activity diminishes, and nothing more dramatic follows. The challenge is that there is currently no reliable way to distinguish a foreshock sequence from a standalone swarm in real time. You can only identify a foreshock sequence after the main shock has already occurred, at which point the information is no longer useful as a warning. This is one of the most frustrating problems in all of earthquake science. What the historical record does tell us is that the Ryukyu region is capable of very large earthquakes. The strongest event recorded in this area struck in 1938 at magnitude 7.7. An earthquake of that size occurring at shallow depth in the modern era would produce a tsunami with the potential to affect Japan, Taiwan, South Korea, and parts of East Asia. Millions of people live along the coastlines that would be in the wave's path. Evacuation infrastructure exists, monitoring systems are in place, and Japan in particular has invested enormously in tsunami preparedness since 2011. None of that makes a magnitude 7+ event a pleasant prospect, but it does mean the region is more prepared for it than almost anywhere else on Earth. Scientists are currently watching this swarm with measured concern rather than alarm. The most probable outcome remains a gradual decline in activity, but measured concern from a seismologist means something specific. It means the data does not allow them to rule out escalation, and they are paying close attention. Meanwhile, several thousand miles to the south, something very different is happening. Something that doesn't produce tsunamis, doesn't threaten coastlines directly, and is classified by scientists in a category of phenomena that we understand less than almost anything else the planet does. Something happening hundreds of kilometers underground, in rock that shouldn't be breaking at all. The Tonga-Kermadec Trench System is one of the most extreme geological features on the surface of this planet. The trench itself plunges to depths of over 10 kilometers below sea level, making it one of the few places on Earth where the ocean floor has been pulled so far down by subducting plates that it approaches the boundary of what we can even measure with standard instruments. The Pacific Plate is being consumed here, dragged beneath the Australian plate at one of the fastest subduction rates on Earth. It is a place of extraordinary violence, conducted at geological timescales, and it produces earthquakes regularly at a wide range of depths. But the 3 earthquakes that struck in this region between February 10th and March 1st, 2026, belong to a specific category that sits in its own unsettling corner of the science. Magnitude 6.2 on February 10th, magnitude 6.0 on February 22nd, magnitude 6.3 on March 1st. These events occurred at depths ranging from approximately 500 to 600 kilometers below the surface. That puts them firmly in the classification scientists call deep focus earthquakes. And if you want to understand why these events generate genuine scientific puzzlement, you need to understand what the Earth looks like at that depth. The outermost layer of the Earth is the crust, which is relatively thin, between 5 and 70 kilometers, depending on whether you're under ocean or continent. Beneath the crust is the mantle, which extends to roughly 2,900 kilometers depth. The upper mantle, from about 60 to 400 kilometers down, consists of rock that behaves semi-plastically under the extraordinary pressures it experiences. At 500 to 600 kilometers depth, you are well into what geologists call the transition zone, a region where pressures are so enormous and temperatures so extreme that the minerals making up the rock actually transform into different crystal structures entirely. Rock doesn't just deform slowly at these depths, it fundamentally changes what it is at an atomic level. This creates a genuine scientific puzzle. Earthquakes occur when rock fractures, when accumulated stress exceeds the strength of the material, and it breaks along a fault plane. But at 500 plus kilometers depth, the pressure acting on rock is so intense that fracture in the traditional sense shouldn't be possible. The rock should deform plastically, flowing slowly rather than snapping. The sheer weight of hundreds of kilometers of material pressing down from above ought to prevent the kind of sudden brittle failure that produces seismic waves. And yet, deep focus earthquakes happen. They have been recorded for over a century. They are real, and scientists still argue about exactly why. Several competing explanations exist, and none of them fully accounts for all the observations. One leading hypothesis involves mineral phase transformations. As subducted rock descends and experiences increasing pressure, minerals like olivine convert to denser crystal structures. This transformation can theoretically create sudden localized instabilities that release energy in a manner resembling a conventional earthquake. Another hypothesis involves dehydration. Oceanic crust carries water bound into its minerals, and as that crust descends and heats up, the water gets released. Pressurized fluids moving through rock can dramatically reduce its effective strength and trigger failure, even in conditions that should prevent it. A third hypothesis, sometimes called thermal runaway instability, proposes that a small amount of frictional heating can make a localized zone of rock dramatically weaker, causing it to shear suddenly. The honest scientific position is that all three mechanisms probably contribute to some degree in some contexts, and that our picture of what's actually happening at these depths is still incomplete. We studied deep earthquakes largely by analyzing the seismic waves they produce and working backward to understand the source. We cannot send instruments there. We cannot sample the material. We are reading a book from the outside, trying to understand the story from the vibrations it sends through the cover. What makes the current Fiji sequence notable is the same pattern we saw in the Japan swarm: escalation. The events moved from 6.2 to 6.0 to 6.3, not a clean escalation, but a sequence that hasn't resolved downward. And this region has shown it can produce earthquakes of extraordinary magnitude at these depths. In 2018, a magnitude 8.2 deep earthquake struck in this same system, the largest deep focus earthquake recorded in decades. The energy released by that single event was staggering. Some researchers looking at the current sequence believe that a magnitude 7 event at this depth in this region is more statistically probable in the near term than the Japan swarm producing a magnitude 7 at the surface. That's not a prediction. That's a probability assessment based on the escalation pattern. There's a difference, though. That difference doesn't always feel significant when you're in the middle of it. Deep earthquakes don't produce tsunamis, and at these depths, their surface effects are typically felt as slow, rolling waves across a wide area rather than violent ground shaking. But they radiate seismic energy throughout the mantle, and that energy travels. Exactly what it does when it arrives at other plate boundaries, and whether it can influence stress on distant fault systems, remains one of the open questions in the field. Which brings us, somewhat inevitably, to a patch of desert in Nevada, and a fault that had been hiding in plain sight for longer than anyone realized. The state of Nevada is, in geological terms, an enormous crumpled mess. And I mean that as a precise scientific description rather than an editorial opinion. The Basin and Range Province, which covers most of Nevada along with parts of Utah, Arizona, and neighboring states, is one of the most heavily faulted regions in North America. The crust here has been stretched, pulled apart horizontally by tectonic forces over millions of years, creating a corrugated pattern of alternating mountain ranges and flat valleys. Every one of those mountain ranges is bounded by faults. Thousands of them. Many have been mapped. Many have not. The Nevada desert is essentially a library of geological hazards, and it turns out some of the volumes were still on the shelf with the spines facing inward. The Warm Springs area sits in central Nevada, east of a town called Tonopah, and takes its name from the hot springs that have been present in the region long enough to give it that designation on maps. Hot springs are a geological clue worth paying attention to because they indicate that the crust in this area is fractured enough to let heated water from depth circulate upward. Fractures mean faults. Faults mean potential seismic activity. But the specific fault that began revealing itself in early March 2026 hadn't produced enough historical activity to be cataloged before the swarm started. Over 100 seismic events have been detected within approximately 50 miles of the Tonopah test range. The largest reached magnitude 4.3 on March 2nd. Additional events came in at magnitude 4.0, 3.9, and 3.5. None of these are particularly large in absolute terms. A magnitude 4 earthquake is felt by people near the epicenter, but rarely causes significant damage. What matters here isn't the size, it's the location. And it's the fact that when seismologists at the Nevada Seismological Lab ran the data, the fault geometry they were seeing didn't match any structure in their existing catalog. The direct quote that circulated in seismological circles was unambiguous. "We didn't know this fault was there." This kind of discovery happens more often than most people realize, and that fact is both reassuring and slightly unsettling, depending on how you look at it. The reassuring interpretation is that we have sensitive enough instruments to detect and characterize previously unknown faults when they become active, which means our monitoring capability is genuinely improving. The unsettling interpretation is that thousands of kilometers of fault lines exist beneath our feet that we haven't mapped yet, and some of them sit beneath populated areas. Earthquakes have a way of introducing us to their home addresses without sending advance notice. The hydrothermal factor in the Warm Springs area adds another layer of complexity. Fluids moving through fractures in the crust can trigger earthquake swarms entirely independently of large-scale tectonic stress. Hot, pressurized water under the ground acts as a lubricant on fault surfaces. It reduces the friction that keeps fault planes locked, allowing them to slip at stress levels that would otherwise be insufficient to cause movement. This mechanism is well documented, and it means the Nevada swarm may be less about regional tectonic stress and more about what's happening in the local plumbing system of the crust, which, incidentally, is also relevant to certain theories about what's happening in the Cascadia system, but we'll get to that. The internet's preferred explanation for the Nevada swarm involved nuclear testing, specifically at the Nevada test site and its environs, including the facility colloquially known among conspiracy enthusiasts as Area 52, not 51, which is to the south, but 52, which is less famous and therefore apparently more sinister. The theory is that underground explosions are triggering the earthquakes. Seismologists have a very clean response to this. Explosion signatures are fundamentally different from tectonic earthquake signatures. When a nuclear device detonates underground, it produces a specific pattern of seismic waves, primarily compressional waves radiating outward in a relatively uniform sphere. Natural earthquakes produce a more complex combination of compressional and shear waves in a pattern that reflects the geometry of the fault and the direction of slip. These signatures are distinguishable with modern instruments, and the Nevada swarm looks like tectonics, not explosions. The mystery is geological, not governmental. Experts looking at this swarm currently consider a major earthquake, magnitude 6 or above, unlikely as a direct consequence of this swarm. The energy levels are too small, the fault too newly identified to have known dimensions, and the hydrothermal triggering mechanism tends to produce diffuse swarms rather than loading toward large events. But here's the thing that should linger. If a fault of unknown size and geometry can materialize out of the Nevada desert with no advance warning, and if over 1,000 faults in the Basin and Range Province remain unmapped, what else is down there? What other surprises are sitting quietly under the ground of the American West, accumulating stress, waiting for the conditions that will finally make them visible? That question gets significantly more uncomfortable when you scale it up to the Pacific Northwest. Because the new Cascadia study didn't just find something we hadn't mapped. It found that the thing we thought we had mapped was something else entirely. Step back from the individual stories for a moment and look at the map as a whole. The Earth's surface is divided into roughly 15 major tectonic plates and a larger number of smaller ones, all moving relative to each other at speeds of centimeters per year, roughly the rate at which your fingernails grow. This movement is driven by convection in the mantle beneath, hot rock rising from depth and cooler rock sinking back down in enormous sluggish cycles. The plates don't move independently and uniformly. They interact at their edges, building stress where they collide, releasing it where they pull apart, and producing complex cascading adjustments across interconnected systems when anything large enough happens anywhere in the network. The Philippine Sea Plate is a useful lens here. This plate is currently experiencing seismic activity on multiple boundaries simultaneously. The Ryukyu Swarm sits on its northwestern edge. The Tonga-Kermadec system, while technically on the Pacific Plate boundary with the Australian Plate, sits within a broader arc of subduction that includes the Pacific Plate's interaction with the Philippine Sea region through the Mariana System to the north. And on March 2nd, the same date as the Nevada Swarm's largest event and the Night of the Blood Moon, a magnitude 6.0 earthquake struck near Japan's volcano islands, also part of the broader Philippine Sea Plate stress environment. Multiple points of the same plate system expressing activity in a compressed time frame is, at minimum, a pattern worth noting, even if its causal significance remains uncertain. The scientific concept relevant here is stress transfer, sometimes called Coulomb stress transfer in more technical literature. The idea is that when one fault moves, it slightly redistributes the stress field in the surrounding crust. Some areas get stress added to them, moving them closer to failure. Other areas get stress relieved, making them temporarily more stable. For faults that are already close to their failure threshold, even a small addition of stress can be enough to trigger an event. This mechanism has been documented convincingly at regional scales. The sequence of earthquakes that followed the 1992 magnitude 7.3 Landers earthquake in California showed clear Coulomb stress triggering of subsequent events in the weeks and months that followed. The contentious question is whether this mechanism operates at the global scale, whether a major earthquake in Japan, say, can meaningfully influence fault stress in Nevada or along the Cascadia zone thousands of miles away. Some researchers argue yes, particularly through the propagation of seismic surface waves that can travel all the way around the planet and dynamically trigger seismicity in regions already near critical stress thresholds. The evidence here is suggestive, but not conclusive. The 2011 Tohoku earthquake was followed by notable seismic activity at geothermally active sites in the United States, including in Nevada. Whether that's causal or coincidental depends on who you ask and which statistical test they prefer. The honest scientific answer about whether the current three-zone cluster is meaningful or coincidental is, we genuinely don't know yet. The cluster is recent enough that the data needed to evaluate it properly is still being collected. Researchers who dismiss it entirely are being incautious in one direction. Researchers who declare imminent global catastrophe are being incautious in the other. The appropriate response is careful attention without conviction, which I recognize is deeply unsatisfying if you were hoping for a cleaner answer. What I can tell you is this. While seismologists were analyzing the Japan swarm, the Fiji sequence, and the Nevada fault, a small group of researchers was publishing a paper that nobody outside of a specific corner of geophysics had been paying much attention to. The paper appeared on February 27, 2026, in a peer-reviewed journal. It was based on data from instruments that have been sitting on the floor of the Pacific Ocean for over a decade, measuring vibrations so subtle they don't register on conventional seismographs. And what those instruments had recorded, accumulated over 13 years and then carefully analyzed, described a Cascadia subduction zone that behaves nothing like the single, unified, sleeping fault that has been described in most public accounts of the Pacific Northwest earthquake threat. The implications of what they found are, depending on how you look at them, either somewhat reassuring or considerably more frightening than the conventional picture. Possibly both at once. That's geophysics for you. The Cascadia subduction zone stretches for approximately 1,000 kilometers along the Pacific coast of North America, running from Northern California through Oregon, Washington State, and up to Vancouver Island in British Columbia, Canada. This is one of the longest subduction zones on the continent, and it is the source of what emergency managers and geologists refer to simply as the Big One, a potential earthquake of magnitude 8.5 to 9.2 that would represent one of the most catastrophic natural disasters in the recorded history of North America. The tectonic setup is conceptually straightforward, even if the details are anything but. The Juan de Fuca plate, a relatively small remnant of what was once a much larger oceanic plate, is being pushed eastward and forced beneath the much larger North American plate at a convergence rate of approximately 4 centimeters per year. That's not fast by subduction standards. In fact, it's rather slow, but it's been happening continuously for millions of years. And slow and continuous in tectonics means enormous amounts of accumulated strain over geological time. What makes Cascadia unusual, and what confused scientists for decades, is how quiet it is. Most active subduction zones are seismically noisy. They produce a steady background of small and moderate earthquakes, reflecting the constant friction and adjustment happening along the plate interface. Japan's subduction zones, South America's subduction zones, the Aleutian Arc in Alaska. All of them rumble regularly, providing scientists with a continuous stream of data about the state of stress on the fault. Cascadia, by contrast, is nearly silent. The zone produces very few earthquakes relative to its length and the convergence rate of the plates involved. For a long time, this silence was interpreted as evidence that Cascadia wasn't a significant hazard, that the plates were sliding past each other relatively smoothly, releasing stress gradually, without the violent stick-and-slip behavior needed to produce catastrophic earthquakes. This interpretation turned out to be badly wrong, and the correction came from an unexpected direction. In the 1980s and 1990s, researchers began finding evidence for a massive earthquake that had struck the Pacific Northwest in the distant past. They found drowned forests along the coast, trees that had sunk suddenly into tidal marshes when coastal land abruptly dropped during a great earthquake. They found layers of tsunami sand deposited inland. They found oral traditions among indigenous peoples of the coast describing sudden catastrophic flooding. And then they found the Japanese tsunami records. On January 26, 1700, which was over 300 years ago, a tsunami struck the coast of Japan with no accompanying earthquake in Japan itself. It was an orphan tsunami, a wave that had traveled all the way across the Pacific from a source earthquake. Japanese historical records document the wave height and the date precisely. Working backward from the tsunami's travel time and characteristics, researchers identified the source as a magnitude 9.0 earthquake on the Cascadia subduction zone, occurring at approximately 9 in the evening Pacific time. The date January 26, 1700, is now one of the most well-documented earthquake events in the geological record of the Pacific Northwest, even though no one alive at the time left a written account on the North American side. The recurrence interval for full margin Cascadia ruptures, events where the entire length of the fault breaks at once, appears to be roughly 450 to 500 years based on the sediment record. The last one was 326 years ago. That number sits in the scientific literature with a kind of quiet weight. The millions of people who now live in Seattle, Portland, Vancouver, and along the Oregon and Washington coasts are occupying real estate that sits directly in the path of what the planet has done before, multiple times, at relatively regular intervals, like a geological clock that nobody can read precisely, but everybody understands is still running. The challenge scientists face is this. With so few earthquakes occurring on the Cascadia fault system, the conventional tools for monitoring fault behavior, studying the frequency and distribution of small earthquakes, identifying precursory swarms, tracking microseismicity, don't work very well. The fault is too quiet. So a group of researchers decided to listen to it in an entirely different way. And what they heard over 13 years of patient listening changed the picture completely. The Ocean Observatory Initiative's Regional Cabled Array and Ocean Networks Canada's Neptune Observatory together represent one of the most ambitious scientific infrastructure projects in the history of Earth science. The Regional Cabled Array alone consists of hundreds of kilometers of fiber optic cable laid across the floor of the Pacific Ocean, off the coasts of Oregon and Washington, connecting a network of instrumented platforms and sensors to shore-based data centers that process their output continuously. Among the instruments connected to this network are broadband seismometers, devices sensitive enough to detect vibrations far too subtle to register as felt earthquakes, recording the constant low-level acoustic and seismic activity of the ocean floor itself. The researchers behind the February 27 study weren't looking at earthquakes in the conventional sense. They were analyzing what scientists call ambient seismic noise, the constant, low-level background vibration of the Earth that comes from ocean waves interacting with the seafloor, from atmospheric pressure changes, from distant storms, from the sum of all the small mechanical energy inputs that the planet absorbs and transmits through its crust every second of every day. This background noise is usually treated as interference to be filtered out when looking for earthquake signals. These researchers treated it as the signal itself. The technique they used relies on a physical property of wave propagation. When seismic waves travel through rock, even background noise waves, their velocity depends on the mechanical properties of the rock they're passing through. Rock that is under high compressive stress transmits waves slightly faster. Rock that has opened microcracks, or that contains pressurized fluids working their way through fractures, transmits waves slightly slower. By measuring how the velocity of ambient seismic noise changed over time between pairs of stations, scientists can track changes in the stress state of the rock between those stations without needing an earthquake to occur. The measurement is expressed as dV over V, which represents the fractional change in seismic velocity, a number that might be a fraction of 1%, but that carries meaningful information about what the rock is doing. 13 years of this data is an extraordinary resource. Most seismic monitoring focuses on events, discrete moments when something happens. This dataset captured the continuous state of the fault system across more than a decade, through all seasons, through tidal cycles, through major distant earthquakes, through slow slip events, through everything the Earth threw at it. The result was a time-resolved picture of stress accumulation and release along the Cascadia fault system, with a level of detail that no previous study had achieved. What the data showed was not what anyone expected to see from a fault that appeared, from the outside, to be uniformly locked and uniformly silent. The Cascadia subduction zone is not behaving as a single entity. It is not loading uniformly toward a single future rupture. It is instead a system of segments with fundamentally different behaviors, some accumulating stress steadily, some releasing it episodically, some apparently channeling fluids through pathways in the sediment that alter the mechanical properties of the fault interface in ways that affect how and when it might eventually fail. The simple picture of one locked fault, one future earthquake, one horizon of catastrophic risk, turned out to be a simplified story about a system that is considerably more complex. And complex, in this particular context, is not the same as reassuring. The core finding of the 2026 Cascadia study can be stated simply, even though the implications take considerably longer to unpack. The Cascadia subduction zone is not one fault. It is several faults with different mechanical behaviors, joined together along their margins, behaving differently from each other at any given point in time, and probably going to behave differently from each other when the eventual rupture occurs. Think of it not as a single steel cable under tension, but as a rope made of threads with different elasticities, some pulling tight, some fraying slightly, some still slack. The northern section of Cascadia, off the coast of Vancouver Island, shows the most consistent and concerning signal in the seismic velocity data. Over the 13-year study period, the seismic wave velocity in this section has been steadily increasing. Increasing velocity means the rock is compacting, becoming denser, more rigid, more tightly closed. That is the physical signature of stress accumulation. The plates are locked together. The Juan de Fuca plate is being driven beneath the North American plate, and the energy of that collision is being stored in the elastic deformation of the crust, rather than being released as seismic activity. This section is, in the language of subduction zone science, highly locked. High locking ratios have been confirmed by geodetic data, GPS measurements showing the ground surface being slowly dragged toward the trench and then rebounding as stress accumulates. The seismic velocity data now adds a 13-year temporal dimension to that picture, showing the locking has been continuous and consistent throughout the study period. The central section of Cascadia, off the coast of Oregon, tells a different story. Here, the seismic velocity data doesn't show steady accumulation. Instead, it shows episodic variations. Periods of stress increase, followed by releases, irregular in their timing and magnitude, corresponding to a phenomenon called episodic tremor and slip, or slow slip events. A slow slip event is essentially an earthquake in slow motion. The fault moves, sometimes by as much as a centimeter over a period of weeks, but instead of releasing its energy in a sudden violent rupture, it releases it gradually, generating a distinctive form of seismic tremor that is detectable by sensitive instruments, but not felt by humans on the surface. The 2016 slow slip event off the coast of Oregon, which the study analyzes in detail, shows how this mechanism works in Cascadia specifically. Over approximately 2 months, a section of the fault moved about 1 centimeter, releasing accumulated stress at a rate slow enough to prevent surface rupture. Researchers identified a network of what they describe as fluid highways in the sediment wedge above the fault, pathways where pressurized water, migrating upward through fractured sediment, was reducing friction on the fault interface and allowing gradual slip to occur. These fluid pathways are not randomly distributed. They follow specific structural features in the sediment and appear to be persistent over the study period, suggesting they are stable features of the fault architecture rather than temporary anomalies. The sediment wedge of an accretionary prism, the pile of scraped-off ocean floor material that accumulates at a subduction zone over millions of years, contains a class of structures called protothrust faults. These are small, incipient fault structures within the sediment that haven't yet fully developed into through-going faults. In the Cascadia system, these structures appear to act as the plumbing network for fluid migration, channeling pressurized pore water from the base of the sediment column toward the surface. The interaction between these fluid pathways and the deeper locked fault interface is one of the key mechanical relationships the study identified, and it's one of the reasons the system is harder to model than a simple locked fault. The picture that emerges from combining the northern and central sections is a fault system with, to borrow a term from behavioral science, multiple personalities. One section is steadily loading, another is periodically self-releasing. The interface between these two behaviors, the transition zone where steady loading gives way to episodic slip, is, in principle, a particularly important location for understanding future rupture behavior. And the question the study raises but cannot yet definitively answer is whether these segments will rupture together in a single full margin event, or whether they might rupture independently, producing a series of large but not catastrophic earthquakes, rather than the single magnitude 9 scenario that dominates most public discussion of the Cascadia hazard. there is a version of this where segmentation is partially good news. And then there is the Seattle problem, which is a different kind of news entirely. The northern section of Cascadia, the portion running off the coast of Vancouver Island and northwestern Washington state, has been accumulating seismic energy without release for longer than any other part of the system. And the 13-year dataset makes this visible in a way it has never been visible before. The seismic velocity increase in this section isn't dramatic. We're talking about fractions of a percent, measured with extraordinary precision over thousands of instrument hours of data. But it is consistent. It is monotonic. It has not reversed or plateaued during the study period. The rock is getting harder, in a sense, because the stress is loading it continuously, closing its pores, pressing its grains together, bringing it closer to the threshold at which the accumulated elastic energy has to go somewhere. This section of the fault is what seismologists call highly coupled, meaning that the Juan de Fuca and North American plates are stuck together at the interface rather than sliding smoothly. The degree of coupling, how stuck they are, is measured through a quantity called the locking ratio. A fully locked fault has a coupling ratio of 1, meaning all the convergence is being stored as elastic strain rather than released as slip. Geodetic studies have shown that the northern Cascadia interface has locking ratios approaching 1 over significant sections of its length. The new seismic velocity data essentially confirms and adds temporal resolution to what the GPS data had already suggested. This section has been fully locked and loading throughout the entire study period, and probably for much longer. The other pieces of the diagnostic picture fit together grimly. The northern section produces almost no microseismicity, no small earthquakes that would indicate gradual stress release. Pore pressure measurements from seafloor boreholes suggest that fluid pressure at the fault interface is elevated, which might seem like it should promote slow slip, but instead appears to be contributing to locking in this particular section. GPS stations on Vancouver Island and the northern Washington coast show the telltale surface deformation pattern of a locked subduction interface. The land is being slowly pulled toward the trench and bowing downward, storing elastic energy that will eventually rebound violently upward during rupture. All of these indicators point to the same conclusion, and it is the same conclusion geophysicists have been reaching about this section for decades, now expressed with greater precision and confidence. The northern section of Cascadia is locked. It has been locked for a long time. It is accumulating strain at the full convergence rate of 4 centimeters per year. It has not found a way to release that strain gradually, and at some point, in a decade, in a century, in a matter of years, it will release it all at once. Vancouver Island, Seattle, and the northern Washington coast sit directly above or adjacent to the section of the fault interface that is doing this most energetically. The study can tell us the mechanical state of the system. It cannot tell us the timing. And the absence of that information is perhaps the most uncomfortable thing about everything we now know. The central section of Cascadia, running off the coast of Oregon and southern Washington, has been releasing pressure in small amounts for years. And the February 2026 study documents exactly how this works at a level of detail that wasn't previously possible. The slow slip mechanism here isn't a mystery. Episodic tremor and slip has been known to occur in Cascadia since the early 2000s, when GPS networks on land became sensitive enough to detect the millimeter-scale surface deformation associated with fault movement, too gradual to generate conventional earthquakes. What the new seafloor data adds is the fluid story underneath. The 2016 slow slip event off Oregon serves as the study's primary case example, and it illustrates a process that is, in its own way, beautiful in mechanical terms, even as it raises concerning questions. Over approximately 2 months, a section of the central Cascadia interface slipped about 1 centimeter. On the surface, this was detectable only by sensitive GPS instruments. On the seafloor, the ambient seismic noise network recorded a complex choreography of velocity changes that told the story of fluid migration. pressurized water moving upward through the sediment column along specific structural pathways, temporarily reducing effective stress on the fault interface, allowing gradual slip to occur. And then, as the fluid redistributed and pressure equalized, the fault relocked and the slow slip stopped. The researchers described these fluid migration pathways as, in their own words, fluid highways, a phrase that is scientifically accurate, and also, if you sit with it long enough, slightly unsettling. These aren't random cracks. They are organized structural features of the sediment wedge that have been guiding fluid movement for long enough to leave their signature in 13 years of seismic velocity data. They are, in a sense, the fault system's pressure release valves, places where accumulated pore pressure can bleed off before it gets high enough to reduce friction, to the point of catastrophic slip. The dual nature of these features is what keeps researchers cautious about calling them reassuring. On one hand, a fault system that periodically releases pressure through slow slip and fluid migration is less likely to accumulate the kind of extreme stress that only resolves through violent rupture. The central Cascadia section has been slowly leaking energy for years. Every centimeter of slow slip is a centimeter of convergence that doesn't have to be resolved in a single terrifying event. On the other hand, elevated pore pressure in a fault zone is also one of the most reliable triggers for earthquake rupture initiation. When fluid pressure gets high enough, it reduces the effective normal stress clamping the fault closed, and the fault can slip, not slowly and gradually, but suddenly and violently. The same mechanism that enables the safety valve can, under the right conditions, become the trigger. Scientists cannot currently predict which of these roles the fluid pathways will play in a future rupture. What they know is that the fluid migration is real, that it is structural and persistent rather than random, and that it creates a fundamentally different mechanical environment in the central section compared to the northern section. The northern section loads steadily and doesn't release. The central section loads and periodically bleeds. These are two different faults joined at their margins, and they will interact with each other in ways that models don't yet fully capture. Whether the leaking section acts as a barrier that stops a northern rupture from propagating southward, limiting the magnitude, or whether it acts as a lubricated pathway that allows rupture to accelerate when it arrives there, is one of the most consequential unanswered questions in the entire field of earthquake hazard science on this continent. The answer determines the difference between a catastrophic regional earthquake and a civilization-scale event. And all of this is happening beneath a coastline where the ground hasn't moved significantly in 326 years, where the geological clock doesn't have an alarm, just a history, where the seismometers are now listening more carefully than they ever have before, picking up signals that were invisible until instruments on the ocean floor started transmitting data up a fiber optic cable and into servers where researchers could finally, after 13 years, see the full picture of what the fault has been quietly doing in the dark. 3 earthquake zones lit up this week under a blood moon, and the internet noticed. But the scientists who truly understand what's at stake are looking at a different screen, watching a different signal. And what it shows them is that the ground beneath the Pacific Northwest has been keeping a secret for a very long time. The question is no longer whether it will speak. The question is only how loud the voice will be when it finally does. The planet is a machine. It runs on timescales that dwarf human civilization. The 300 years since the last Cascadia rupture is, in geological terms, a pause between breaths. The 1,200 earthquakes shaking the Ryukyu Islands right now are a tremor in a system that has been convulsing for millions of years. The deep earthquakes south of Fiji are rock transforming under pressures our instruments can detect, but our intuitions cannot truly grasp. The Nevada fault that materialized out of nowhere this week was always there. We simply didn't know to look. And that, perhaps, is the thing worth sitting with when the video ends and the screen goes dark. We are not watching the Earth become more dangerous. We are becoming better at understanding how dangerous it has always been. The map is not changing. We are finally learning how to read it.